Okay, at this point we have reached the end of the chemical equilibrium chapter, and the last thing that we need to discuss is the Le Chatelier's principle. And the Le Chatelier's principle pretty much is telling you, in order to make predictions about what happens to an equilibrium when you make some changes, when you kind of distort that equilibrium. And the picture that I pick here is that this is an elephant doing a good job in doing equilibrium over a ball. Okay, whether that's real or not, that's a different story. But think in terms of what would happen to that elephant if, say, let's give him a little push in that direction. What's going to happen to him? So pretty much you may predict if you do a push in that direction, from left to the right, then the elephant most likely will fall down in this direction, right? So, but what if we given a little push in this direction, okay, from the right to the left? Then most likely the elephant will fall in that direction. So that's the point with Le Chatelier's principle. Now we are going to apply this principle to chemical reactions, and then we are going to explore different disturbances, what they do to the equilibrium. And the point here is to determine if that disturbance is going to cause the equilibrium to shift to the left or to shift to the right. Okay, so that's all there is about this. And this section is mostly conceptual. There is nothing to calculate but predictions to make. All that we are looking for here is whether the equilibrium is moving to the left or moving to the right. So here is about, remember, moving to the left, moving to the right, it implies that the concentrations will change in such a way that you are either favoring the products or you are favoring the reactants. Okay, and here remember, we are doing something to the equilibrium, and the equilibrium will move. You're gonna reach equilibrium again, but the position of that equilibrium is gonna be different. For example, at the equilibrium you may have a condition in which the concentrations are equal. It's not a requirement for the concentrations to be equal, but if you cause a disturbance and the concentration changes, then you may have a higher concentration of products, a lower concentration of reactants, but still they're going to be at equilibrium. Okay, it all depends on what the disturbance is. So the equilibrium is not going to be exactly the same equilibrium that you had before, but it's going to be in equilibrium conditions nonetheless. Okay, so the Le Chatelier's principle is a principle that we use to predict what happens to the equilibrium when you cause a disturbance. And in a nutshell, what it means is that whatever disturbance you make, the equilibrium will respond in such a way that it will minimize the impact of that change. Okay, so we want to minimize that disturbance, whatever it is. Okay, so for example, if you add reactants, well, what happens with reactants? So remember, if we apply chemical kinetics here, if you increase the concentration of the reactants, the rate of the reaction is going to increase, right? That means the forward reaction will increase. Therefore, adding more reactants, the impact that it's going to have is, well, to speed up the forward direction, meaning you will produce more products. Therefore, if you are favoring the products, then increasing the reactant concentration will shift the equilibrium to the right. Okay, now there is a catch, because we have gone through heterogeneous equilibrium, and in heterogeneous equilibrium it just so happened that if it's a solid or a liquid, pure solid or pure liquid, there is no impact. So if you're adding more reactant and the reactant is a solid, nothing is going to happen. Okay, now that reaction will shift to the right, but it won't be indefinitely, because you're going to reach a new equilibrium situation. An equilibrium situation in which the reactant concentration will decrease a little bit from that increase that you had, and the concentration of the products will increase. Now, what happens to the value of K? Yeah, you are changing the equilibrium position, you are changing the concentration, but nothing happens to the value of K. Okay, why? Because you are adding a reactant. It could be if you add a product, it could be even if you take out reactant or you take out product, the value of K will not change, because K pretty much depends on the temperature. As long as you keep the temperature constant, the value of K will not change. Now, if you remove reactant, okay, removing reactants means you are decreasing the concentration of the reactant, correct? So think in terms of Q, right? Now, if you decrease A, and if you were in an equilibrium position, then you have to make it in such a way that B will decrease and A will increase to return to the equilibrium condition. Okay? So, again, if it's not a solid, if it's not a liquid, there would be an impact. If the solid and liquid will have no impact whether you add more or you take out the solid or the liquid. But if it's something that the concentration will change, then if you remove the reactant, then the equilibrium will shift on towards the left. It will favor the reactants, because removing the reactants, you have the impact was to remove the reactant. Okay, to minimize the impact of that removal, then you have to increase the concentration of the reactant. That's why the reaction, the equilibrium will shift to the left. Okay, again, shift to the left until the equilibrium is restored. That means you are going to increase the concentration of the reactant a little bit, and then you are going to decrease the concentration of the products a little bit. Once again, the value of K does not change. And if we are looking at this from the point of view of a reactant, but if you do from the point of view of a product, it's exactly the same principle. In this case, if you add more product, then you increase the rate of the reverse reaction, and then you shift the equilibrium towards the left, favoring the products. If you remove products, then you are shifting the equilibrium towards the right, favoring the products, because you have to replenish what was removed. Therefore, you will increase the concentration of the product from that point from the point that it was removed, and the concentration of the reactants will decrease accordingly. Okay? So we can summarize everything that we have said. Okay, it could be reactants, it could be products, it could be that you are adding more of each of any of those, or that you are removing some of those. We can summarize this into saying that the equilibrium will shift away from the side that you are adding, and it will shift towards the side in which you are removing. So let's take a look at that. So we have not A plus B, A that goes to B. Okay? And let's say that we add more B. You are adding more B, therefore your equilibrium will move away from that point. So if the side that you are adding more is the product side, your equilibrium will move away, so it will favor reactants. Okay? Likewise, if you have your equilibrium and then you are removing B, okay, because you are removing, then the equilibrium will shift towards the side where you're removing. If you're removing on the product side, the equilibrium will shift in the products towards the product side. Okay, so that's a summary. When you are changing concentrations, if you add, move away. If you remove, it moves towards. Okay, so that's the simplest way to remember what happens if you change the concentrations. Now, concentrations are not the only way in which you can do that. This is another example. I don't want to look at this example. I prefer to look at this one. Okay, because this is a graphical view of what's happening. So this is your initial equilibrium condition. A certain concentration of N2O4 and a certain concentration of NO2. In this particular case, you are adding more NO2. So the concentration increase up to that point. Okay, so this is the point of disturbance, and you added more product. So the equilibrium will shift away from that addition. It means the concentration of NO2 is decreasing, and the concentration of N2O4 is increasing. Okay, up to what point? Until the equilibrium is reestablished. Okay, so that's the meaning of these graphs. In the second graph, you are adding N2O4, and as such, then the reaction is shifting right. Okay, in this case, the concentration of N2O4 increased. The end result is that the concentration of N2O has to increase, and the concentration of N2O4 had to decrease. Up to what point? Up to the point in which you reestablish the equilibrium. Okay, so that's the meaning of these two graphs here. Okay, once again, the concentration, the equilibrium will shift away from the side in which you are adding, and it will shift towards the side in which you are removing. Okay, so that's the bottom line here. Now, what happens? How do we use this in a practical approach? So we have this equilibrium, and what happens if you add more CO2? So what happens if we increase CO2 here? Okay, CO2 is a gas. Therefore, if you increase CO2, you are adding on the product side, so you are shifting to the left. Now, the second one is asking you, what if you increase the amount of CaCO3? Now, CaCO3, calcium carbonate, is a solid. So if you increase this, then nothing happens because it's a solid. Okay, solids and liquids, pure solids and pure liquids, have no impact on the equilibrium position. Nothing happens. If you remove, if you add, nothing is going to happen. Okay, so that's the explanation to the previous case. In this one, now the first case is what happens if you increase the concentration of, you add more bromine to the reaction, and you are adding that to the product side. Therefore, if you are adding, then the equilibrium move away, so it's shifting left. And the second question is, what happens if you add more BRNO, which is here? Now, this is a gas. This will have an impact. Therefore, if you increase the concentration, if you add more of this, the reaction will shift to the right, because you are moving away from the side in which you are adding. If you are adding to the reactant side, then the equilibrium will shift towards the product. If you are adding to the product side, then the equilibrium is shifting towards the reactants. Now, what happens if you add gases to the reaction. Okay, it all comes to the partial pressures. Okay, generally speaking, if you add a gas to equilibrium reaction, then it increases its partial pressure, and if it's a reactant, then you are increasing. If you increase the partial pressure, you are increasing the amount of that gas, of that particular gas. If it's a reactant, then the equilibrium will shift towards the products, or in other words, towards the right. And that's because you're increasing the partial pressure. You increase the amount, you increase the partial pressure, you increase the concentration. Okay? If the gas is inert, if it doesn't participate in the reaction, okay? Doesn't necessarily have to be inert, it's just that it doesn't participate in the reaction, then there is no effect. There is no impact on the partial pressures. It's not affecting the volume. It might affect the total pressure of the system, but because you are using the partial pressures in the equation, then inert gases have no impact. Okay, let's write that down. Inert gases have no impact. It will not affect the equilibrium. Okay? Gaseous products, gaseous reactants will have the impact pretty much the same as if you were working with concentrations. Volume change, again, it comes to whether the concentration is being affected, or the concentration is affected. Okay, so if you decrease the volume, you are increasing partial pressures. Okay, if it's a solution, I mean, that happens. The volume will affect if you have reactions in the gas phase. Okay, because it will increase the partial pressure. But if you are working with solutions, generally speaking, it has no impact because the concentration in the solution will keep constant. So now, what's really important here, I mean, if it's working with solutions, you can forget about it, but if most likely when we are applying this Le Chatelier principle, we are working with mixtures in the gas phase. Now, this is really important to remember. If you decrease the volume, then you have to look at the number of gas molecules that you have in the reaction. Okay? If you decrease the volume, you are favoring the side with the fewer gas molecules. Let's use, for example, this. If you have a gas that goes to B, let's put 2B in the gas phase, you have 1 mole of gas, and yes, I know it doesn't sound very good, and 2 moles of gas here. Okay, if you decrease the volume, the side with the least amount of gas is the reactant side, so it will shift in that direction. Okay, if the volume goes down. Okay, if the volume goes up, then if you increase the volume, then you are favoring the side with the most molecules of gas. Okay, so for now, let's skip this one. Okay, reducing the volume will have the impact of increasing the partial pressures, increasing the concentrations for that matter. So the total number of gas will have a higher concentration in that volume, and therefore you will shift the reaction towards the side with the least amount of gas, or the least number of molecules of gas. Okay, so this is a graphical representation of what's happening here. Okay, so if you decrease the volume by increasing the pressure or doing something else, you have 4 moles of gas in that side. You have 2 moles here. Okay, so if you decrease the volume, basically you have less room for those 4 moles of gas. Okay, so they are kind of uncomfortable, so they want to have more room, so you are increasing the pressure there. Then the impact on the equilibrium is, well, if the initial impact by reducing the volume is an increase in pressure, so the system, your equilibrium, will respond in such a way that it will decrease the pressure. How will it decrease the pressure? By going to the side with the least number of moles of gas. Okay, so in that way, by increasing the number of products, by decreasing the number of products in the gas phase, then it will relieve the pressure. So that's why it shifts towards, decreasing the volume will shift towards the side with the least number of moles of gas. And the opposite is true. Okay, so if you decrease the pressure, if you decrease the volume, which will decrease the pressure, then you want to replenish the pressure that you had before, and the way to do so is to increase the number of particles. So still here you have 4 moles. 4 moles will provide higher pressure than those 2 moles. Okay, so you will increase this side so that you increase the pressure as a response to the increasing volume, and therefore the decreasing pressure. Okay, so now we have this case. How do we apply that to a chemical reaction? So let's take a look at how many moles of gas you have at each side of the reaction. Okay, so you have here, we are dividing there. You have a solid, so there are 0 moles of gas here. And this is 0. And then you have 3 moles of gas here. So you have 3 moles of gas on the product side, you have nothing on the reactant side. And the effect here is, if you decrease the volume, what is going to happen? Okay, if you decrease the volume, you will increase the pressure. So if there are no gases here, then you will be shifting the reaction in that direction. Okay, what happens if you increase the volume? Increasing the volume, well, now you're favoring the side with the more moles of gas, so it will shift in that direction. And if you add an inner gas, if it's not participating in the reaction, then nothing happens. Okay, in order for a gas to cause an impact on the chemical equilibrium, then it has to be an active gas, something that is actually part of the reaction. If not, there is nothing there, it won't be an impact there. Okay, so this is the explanation to what we were discussing on the previous reaction. So how about this one? If we decrease the volume here, or if you increase the volume. So let's do this one first. What happens if we decrease the volume of this reaction? Okay, and then we have 1 plus 2, that's 3 moles here, and then you have 2 moles there. If you decrease the volume, then you are favoring the side with the least number of moles of gas, which is the product side. And if you increase the volume, well, the opposite is true. Okay, if you increase the volume, you are favoring the side with the highest amount of moles of gas, so the reaction will shift in that direction. Okay, now this is probably one of the most tricky ones. What happens with temperature? Because with temperature, it will depend on whether the reaction is exothermic or endothermic. And for this part, it could be very useful if you consider, because heat is not exactly a matter that you can add to the reaction, right? So you cannot really explain it by increasing the reactants or increasing the products, because it's not exactly part of the reaction. However, for practical purposes, when applying the Chatelier's principle, we can actually consider it as part of the reaction. Yes, it's heat generated or heat absorbed for the reaction, but whatever the case is, you can use it as if it was part of the reaction. So if we have an exothermic reaction, like in this case, oops, right? Exothermic reactions release heat. Therefore, heat is a product for an exothermic reaction. Therefore, you have heat here. You can just write it, or you can just put Q, but it's in the product side, okay? And once you see it that way, then it's easier to picture what happens with temperature, because increasing the temperature is equivalent to add heat. Okay? If you increase temperature, it's equivalent to add heat. You decrease temperature, you remove heat. Therefore, here, if you add heat, it means you are increasing this, and you are increasing something in the product side. Therefore, the response of your equilibrium is to move away from that side. Therefore, adding heat in an exothermic reaction will shift the equilibrium towards the reactants. Okay? So, and therefore, you haven't add any of the reactants, you haven't add any of the products. So there is something important here, okay? Because you are increasing the temperature, you are not changing the amount of matter that you have in that reaction, but the concentrations will change. So in this particular case, for an exothermic reaction, if you add heat, you are decreasing the concentration of products, and you are increasing the concentration of reactants. Therefore, if temperature increases for an exothermic reaction, K decreases. Okay? And if the temperature decreases, okay, meaning, let's write that down here. If you remove heat, then the reaction shifting that way. Therefore, decreasing the temperature will cause K to increase. Okay, this is for exothermic reactions. And I want you to have this very, very clear. Why? Because if this is true for exothermic reactions, the opposite is true for the endothermic reactions, and we're going to see that in a minute. Okay, so again, adding heat to an exothermic reaction decrease the products. You are moving away from disturbance. Okay, heat is part of the products in an exothermic reaction. If you add heat, it is equivalent to adding more product to that reaction, and therefore the reaction will shift to the left. Now for endothermic reactions, now heat is here. Heat is part of the reactant. Okay, so if you add heat to endothermic reaction, then you will shift the reaction towards the products. Okay, because the heat is in the reactant side, you are increasing the reactant. The disturbance is in such a way that to minimize it, you have to produce more products. Okay, so in this case, now if we see this from the point of view of K, for an endothermic reaction, if you increase the temperature because you are increasing the amount of products, then K will increase, and if you decrease temperature, then K will decrease. This is for endothermic reactions. And once again, I want you to have this very, very clear because they are opposites. Okay, what happens to the exothermic reactions by adding or removing heat is the opposite of what happens with endothermic reactions, and you need to be really clear with this. So here in summary, so if you have an endothermic reaction versus an exothermic reaction, okay, if you increase the temperature or if you decrease the temperature, if you increase the temperature in an endothermic reaction, the equilibrium shifts right and K increases. And if you decrease the temperature in an endothermic reaction, the equilibrium shifts left and K decreases. Now for an exothermic, it's the opposite. If you increase the temperature in an exothermic reaction, the equilibrium will shift left and K will decrease. And if you decrease the temperature in an exothermic reaction, then the equilibrium will shift right and K will increase. Okay, so this is a table that I want you to be really clear with. Okay, endothermic, exothermic reactions. Something happened to K. The concentrations change, of course, but that's because K is changing. It's dependent on the temperature. Okay, more on how dependent on the temperature and how you can calculate that, that's down the road. But for now, this is what you need to remember. So in this particular case, we have an endothermic reaction. What happens if you increase the temperature in this reaction? It's endothermic, right? So if it's endothermic, then it goes here. So increasing the temperature will cause the reaction to go in that direction. And decreasing the temperature will cause the reaction to go in that direction. Okay? Same thing here. If this reaction is exothermic, then we can just add heat here. So if you increase the temperature of this reaction, then the reaction will shift in that direction. Okay, that's increasing temperature. And if you decrease the temperature, okay, you are removing heat, then the reaction shifts in that direction. Okay, the last factor to cause a disturbance on a reaction is the use of catalyst. However, catalyst is the easiest to predict because nothing happens. The mechanism of action of a catalyst is such that it will accelerate both the forward and the reverse direction reactions. So just adding the catalyst will not change the position of the equilibrium. It will just change the time you require to reach the equilibrium. So just remember this: catalysts have no effect on the position of the equilibrium. It only have effect on the timing, how long it takes to reach equilibrium, but not what position the equilibrium is. Okay, so that's it for Le Chatelier's principle. As I said, there is no calculations here, but it's all about predictions. What happens to the equilibrium, the position of the equilibrium, if you produce a disturbance? How can you produce a disturbance of the equilibrium? Changing the concentrations either by adding or removing, changing the volume, changing the pressure, where pressure and volume are related to each other. Okay, and it's all about the moles of gas that you have at each side of the reaction. By the way, if you change the volume and the number of moles of gas at both sides is the same, then there is no impact. Okay, just a friendly reminder there. And then you have temperature. Temperature is the trickiest one because you have exothermic and endothermic reactions, and then you have to pay attention to what case you are in. Whatever happens to an exothermic reaction is the opposite for an endothermic reaction, and then you have to be careful with that. Last but not least, if you have catalyst, there is no impact, so you have nothing to worry about catalyst. Okay, so this is the end of chapter 15. Next up, I believe, is acids and bases, and still it's all about chemical equilibrium applied to a particular system.